Hello and welcome to another video of Grokking the Coding Interview. We are going through the breadth first search approach for the binary trees. And in this video, we'll have a look at level averages in a binary tree, which is classified as an easy problem. So let's get started with the problem statement. Given a binary tree, populate an array to represent the averages of all its levels. So as you see, it seems like right away, right off, because we have worked on other problems previously, it seems like a pretty straightforward problem where we keep our approach exactly the same. So we calculate or we create an array with all the nodes at each level, and instead of pushing that array into the result array, we simply uh, calculate an average of that level array and then push that average into the result array. So everything else remains the same. We just have another additional step of processing and calculating that average. So let's quickly get started and see if we can implement it right off the bat. So from we go ahead and import DQ collections. Again, the same standard exercise. If the root is none, we return the result. We want the queue, which will be dq. We want to push the root into the queue, and we want an outer loop while the queue is not empty. Okay, let me push that out a bit so we have more space. Okay, same exercise as we had here. We do not have to alternate or we do not have to do anything else. So we just want the level size, which will be length of the queue. We want the level nodes, which will be a list because we do not care about or we do not want to push anything to the front. It can be a list, but if we had to push it to the front, we'll go ahead and use a queue. And for underscore in range, level size, we get the current node, which is q dot pop left. I think it actually can be more optimal instead of first creating the array and calculating the node. So what we can do is we can do away with this level nodes entirely. We can keep a track of running sum for that level, and we can just add the running sum, add the value of the current node into the running sum, and we simply go ahead once we have that sum result dot append running sum by level size. And this should actually give us the answer which you're looking for. I hope we do not have any conditions about rounding off it to the closest number. No, so maybe let's just to be a bit anyways. Okay. So I just used the round one to round it off to the first decimal place, which is what I'm seeing here. Okay, let's try to. So we have the running sum. Once we push out a node, we add it into the running sum. At the end, we divide this running sum by the level size, and it should give us the average for that level. And we are just pushing it into the result. And this should provide us with the answer we are looking for. Let's try to run it and see if we are missing something here. We are. If root is should be is, should not be in. So we only have a single average. This is interesting. We are not append. Okay, this is terrible. So if uh, current node left, we want to append in the queue the current node dot left. If current node dot right, and we want to append in the queue current node dot right. And yeah, okay, this should actually work. That was a bit. We missed out the entire traverse to calculate the averages. Funny. Okay, let's see if this would work fine. We are getting the current node. Okay. 4 and 7.5. 12, 4 and 7.5. How are we getting a 7.5 here? How are we getting a 7.5 here? 15, 17, 17 is 26. 26 by 4. Let's see what our running sum is at each level. Second, we have 8, which is fine. And here, for us, it's 15. Are we only aggregating this node here? What are we missing out here? Uh, the print level size. Yeah, this is actually a bit. Oops, this should be inside the for loop actually. Okay, this should give us the answer we are looking for. Yeah, exactly. Okay, that took slightly longer than we expected, but let's quickly speak about runtime and space complexity of our implementation. Again, we are essentially going through all the elements once. So this will be O of n. So runtime will be O of n. When it comes to space complexity, again, don't think anything changes as such. It'll be O of n, and then we have results, which will be the number of levels in the tree. So worst case scenario, O of n. Okay, I hope you found the explanation clear. Please let me know in case I can improve anywhere, or if something was not clear. Until the next video, have a great day.